Good morning, everybody. So we have seen the first law and the components of first law, namely heat and work and energy, basically. So now we'll be focusing on heat at constant pressure, which is enthalpy. In that, we'll be seeing in detail how to calculate enthalpy, the different forms of enthalpy, and what is its significance in, say, a chemical reaction. Or so.
Sir,
Yes, please.
after the class, I have a one doubt, sir.
Hmm.
Sir, during analysis of Gibbs free energy, sir.
During
Sir, analysis of Gibbs free energy.
Gibbs free energy. Okay.
Yes, sir. Which type of gas we are actually used in the system?
We didn't use any particular system. If you talk about the reversible work done, we have used ideal gas.
Sir, if we use sir ideal gas, then sir, how at constant temperature and pressure? Sir, how at constant temperature DO cannot become zero?
How at constant pressure?
Constant temperature.
Constant temperature?
DU cannot become zero, sir. Why DU not zero, sir?
Because
DU
pressure is
means, sir,
also constant.
sir, I do not understand that, sir.
So please understand that at constant temperature, du is zero.
Yes, sir.
At constant temperature and pressure also du is zero.
Yes, sir.
Now, what is the reason?
Because, sir, suppose, sir, sir, if the process is reversible, sir, whatever we heat given to the system, that heat actually utilized to doing work means, sir, Q equals to W.
Mm-hmm.
So that temperature and pressure remain constant because so internal energy or change also be zero, sir.
So at constant temperature, pressure, and whatever is constant, you are telling always du is zero.
Yes. Um,
Means at
yes,
constant temperature also du is zero. Constant temperature and pressure also du is zero. Any other thing you keep constant also du is zero. That's what you're telling.
sir, because the temperature is constant.
That's what. So whatever is constant, irrespective of whether others are constant or not, if temperature is constant, du is zero. That's what you're telling.
Yes, sir, because sir, whatever input actually utilized to doing work, whatever the external pressure
Hmm.
are acting, that external pressure are actually if the work done is done, then sir, it will get reduced or not reduced, sir. It will be same, sir.
Whatever the input we give, it is used to change what?
Sir, volume of the system.
Volume of the system. Whatever the pressure is there, that what about that one?
Sir, suppose, sir, if we give the heat, then inside the ideal gas will means, sir, internal energy will increase, and
Mhm.
due to that, that gas will do some work. So that work actually utilized to increasing the volume and
You are telling
um,
again same thing now. Whatever input is given, that is done to whatever
sir,
input.
can you tell me, sir, why not zero, sir?
That's what. No, du is zero at constant temperature only.
Why
In a
not, sir,
fixed
in pressure?
in a fixed volume.
Yes, sir.
So if pressure is also fixed, what does it mean? The volume is expanding only, no?
Yes, sir.
So normally, if you take a container and you have a fixed volume, we are not changing the volume. Okay. And in fact, if you remember, I gave a homework for people to find that out because nobody answered them. So if you are heating the system, okay,
Yes, sir.
and the gas is not able to go anywhere, whatever the heat that you give, that
Yes,
is
sir.
heat, correct?
Yes, sir. Yes, sir.
Now, if you have a movable piston,
Yes, sir.
some constant external pressure, okay, and you are trying to keep the temperature constant. How do you keep the temperature constant?
Sir,
Temperature and
temperature.
pressure are both constant. Temperature is also constant. Pressure is also constant. How do you keep both constant? Can you tell? Can you think and tell how do you keep both constant?
Sir, because sir, it is closed system, then we can only increase the volume.
Huh.
Otherwise, we can give some amount of gas also.
No, no, that is not allowed. It's a closed system we are talking about. So PV is equal to nRT. So P by T is equal to nR by V. So if this is constant, then obviously n we are not changing. So n by r also should be constant. No?
Yes, sir.
Then everything is constant. You said volume we can change. No? So if P is
But sir, we give the
constant,
external heat also.
hmm?
So we give also external heat, sir.
Correct. We are giving external heat. I'm agreeing to that one. But what about the equation of state? Then equation of state is not valid.
It's a valid, sir.
No, and they don't confuse. So
So
pressure is
what is?
constant. Pressure is constant.
Yes, sir.
Temperature is constant.
Yes, sir.
PV equal to nRT. P by T is constant. So N by
Yes, sir.
R, NR by V is also constant.
But sir, V is not constant.
Why is not? Then what is the fallacy here? Or what is the
Okay.
what is the
Then
problem?
then P or T need to be changed, sir.
No, I will tell you. You have answered the question, but exactly you are not answering. Whatever heat is given, okay, it is doing two types of changes. It is increasing the internal energy also because only temperature is constant. Then you can say that the du is zero. Pressure is also constant. Okay. So the given input of heat is doing two types. One, it is doing the work also against the external pressure, and it is increasing the internal energy also.
Sir, but when we give heat, sir, uh, that heat is utilized to doing work means some amount of internal energy also decreases, sir.
Increases or decreases? You are heating.
Decreases, sir.
You are heating.
Sir, P, yes, sir, heating, then, sir, it is actually expanding.
Hmm.
Then whatever the P external, it is actually constant, sir.
Hmm. It is
Uh,
expanding against the constant pressure.
yes, sir.
Hmm. So whatever the heat input is there, well, it is used to do two types of work. In fact, it is expressed, you know this equation, right?
Yes, sir.
Maxwell's equation.
Yes, sir.
Uh, Now you are telling that, see here, U is a function of
S and B.
entropy and volume.
Yes, sir.
Now, where your concept of temperature and pressure is constant, so U is zero is coming. Can you tell that one?
Okay, you are trying to tell me that in here the volume is expanding,
Hmm.
so you actually function of volume, then also you actually changing, and
Changes.
also,
Yeah.
sir, and
Yeah.
entropy also system is because of.
Absolutely.
Okay, sir.
Absolutely. Got your point, no?
Yes,
And
sir.
in fact, you are keeping temperature and pressure constant, no? They are only coefficients.
Yes, sir. Understood, sir. Understood.
Okay. Clear any doubt? Okay.
Sir,
Hmm. Yes, please.
um, uh, in that question, sir,
Mhm.
according to the questions PV equals to nRT, that you say that if temperature and pressure is also constant, then volume is also constant.
Uh,
Then how to volume varies?
no, no, this is valid only when there is no external heating. Here it is not valid because you are heating externally. So this is a continuously changing equation. P by T values are changing continuously. You are providing external heat now. PV equal to nRT is the equation of state of an ideal gas under no changes in the external conditions. Here it is not valid because you are actually heating and also applying the external pressure. It is valid at a given point of time, not throughout time. At a given point, just at the snapshot, this is valid.
For instant moment. Okay, sir, thank you.
Right. So coming back, anyway, good doubts people are asking. At least people are thinking something good. So, in fact, still my question is unanswered, Nandi. Cp minus Cv is equal to R, the derivation. This is actually Q minus W is equal to delta U. Correct now? So, this is NCP delta T. This is P delta V, you can say. And this is NCV delta T. P delta V is NR delta T. So Cp minus Cv is equal to R. That's what we have derived. How in constant pressure we wrote this one? Nobody told till date. This homework remains. Please think and let me know. Okay. Right. Let's start. Enthalpy. Enthalpy introduction already given to you. Enthalpy is heat at constant pressure. Right. So please write down. Enthalpy is heat at constant pressure. Enthalpy is heat at constant pressure. So we write now H is equal to U plus P. So U is the internal energy. P is the pressure. V is the volume.
Sorry, heat of any system is, can we say that is, this is enthalpy?
Not any system. Any system at constant pressure. You can say yes. Right.
In MCQ, sir, I see that what is enthalpy? So three options, four options that's given there.
Mhm.
Heat of any system, entropy of any system, phase of any system, or none of this. And
Heat of any system, entropy of any system. Third option.
phase of any system. That's not be
Fourth
possible.
option.
Anoti, not of.
So it is a heat of any system actually at constant pressure should be written. Then
But sir, the conditions not given here.
uh,
Conditions are
it's
not
not given.
given.
Not given, then that's not correct actually. Okay. It's not correct. So NOT, none of the above should be the correct. Right. Next point, please, Adam. There are four types of enthalpies. There are four types of enthalpies. First one, thermal enthalpy. Second one, phase transformation enthalpy. Or you can say latent heat. Formation enthalpy and reaction enthalpy. So these are the four types of enthalpy that we talk about. And this entire chapter, we will be seeing each of these entropies. Okay. We will start with the simplest entropy, sorry, enthalpy. So, which is thermal enthalpy. Thermal enthalpy, all of you know, you have been studying since your childhood, that one. So, please write thermal enthalpy. The heat absorbed or given out at constant pressure. The heat absorbed or given out at constant pressure by a system causes the change in the enthalpy, change in the enthalpy given by the following formula. Given by the following formula. So we have derived this earlier, but we will expand it in detail. So dH is equal to Ncp dt. This is the formula for thermal enthalpy. Please remember that heat at constant pressure is a state function. We have proved that as well. Okay. Now, if you want the heat at a temperature T, what do? You have to integrate. So heat at temperature T, this is equal to H naught plus integral 0 to T Ncp dt. Okay. What is H naught? H naught is enthalpy at 0 Kelvin. Does heat exist at 0 Kelvin? Absolutely yes. In the form of what? In the form of potential energy. We saw that in the basics itself, right? So internal energy consists of translational, rotational, vibrational, and potential energies. And your total heat, which is enthalpy, depends on internal energy, because how? H is equal to U plus PV. So H depends on U. Okay, H depends on U. So if there is interaction, if at all there is interaction, then H naught will be non-zero. If suppose there is no interaction, then okay, you can say H naught is 0 at 0 Kelvin. But it need not be 0. That's what I'm saying. It's not compulsorily 0. Okay. It's not compulsorily 0. It can be 0, cannot be 0, but it is not compulsorily 0. So H is equal to U plus PV. We say U is U naught plus 0 to T NCV dt. We say. Now, please understand that your U naught, okay, U naught, it depends on multiple things. So what is U naught? So U naught is a function of kinetic energy, rotational energy, vibrational energy, potential energy. The potential energy at 0 Kelvin need not be 0. We have seen this in physical metallurgy, batch 1. Since P naught is non-zero, you will see that U naught is also non-zero. Since U naught is non-zero, your H naught need not be 0. Right, please take this down.
Sir, one question, sir.
Yeah, please ask.
Sir, the U naught means, sir, potential energy at 0 Kelvin.
U naught is basically the potential energy at 0 Kelvin. Absolutely.
Sir, at 0 Kelvin, we know that there are no kinetic energy, rotational energy, vibrational energy. Only the interaction between the atoms are possible. That's why U naught is not 0. Then why the U naught is a function of kinetic energy, rotational energy, vibrational energy? Instead of U naught should be function of potential energy, and total U should be a function of kinetic energy, rotational energy, vibrational energy, and potential energy.
So yeah, I understood. So that is just the way of writing. So what I mean to say is this is U. of which a specific value is U0.
Okay, sir.
Hmm.
Sir, and sir, H naught and U naught has any relation like H equals to U plus PV?
They have the relation. See, if there is some work being done at 0 Kelvin, okay, then they have a relation. If there is no work, then H0 and U0 are same.
Okay, sir.
Okay. So let's see the formula. This is at a given temperature, you are starting at 0 Kelvin. Now, what if you are not starting at 0 Kelvin exactly? You want between two different temperatures. You want the enthalpy at two different temperatures. Right. Please write down. For a homogeneous or unary closed system, for a homogeneous or a unary closed system, the thermal enthalpy change when the temperature changes from T1 to T2 is given by you know the answer, integral H1 to H2 dH is integral T1 to T2 NCP dt. Now delta H we call H2 minus H1. It is integral T1 to T2 NCP dt. Of course, if your value of Cp is not dependent on temperature, value of Cp is not dependent on temperature, then you can pull out that Cp outside, then you can write NCP delta T, right? So if Cp is not a function of temperature, then you can write delta H is NCP integral T1 to T2 dt. So you can write delta H is equal to NCP T2 minus T. Please remember that always the temperature should be in Kelvin scale. Absolutely.
Sir,
Yes.
sir, in here, sir, pressure is not mandatory.
Pressure.
The pressure function, sir,
Cp is
is not.
written, na?
But sir, if the substance is solid, Cp and Cv are both same.
For what?
Sir, substance is solid. If sir, suppose substance means
Solid
if
is
the
there. Solid
yes,
is there. Okay. So please understand that for solids, there is a relation between Cp and Cv. In fact, we will be deriving that as well for solids. It is based on the thermal expansion and other things. Relation is there. Dulong-Petit law. Have you heard?
Yes, sir.
Some based on that one relation is there. We'll be deriving that in Maxwell's equation. In fact, gate question had come on that, I think 2023.
Okay, sir. Sir, in here, sir, actually you take CP, so that CP is molar heat capacity at constant pressure. So then the constant pressure is actually came into picture.
Correct. Right. Please take this down. We'll do one problem.
Hello, sir.
Yes, please.
So we know that the CP is a function of temperature also.
Hmm.
So
Correct.
here that you write that CP does not depend on the, so is a function,
No,
not
no,
a function
no.
of
I'm telling if na, if CP is not
oh,
yeah.
according to questions or
According
problems.
to question, absolutely. According to question only,
Okay, okay,
yeah.
okay,
Because
okay.
see, for some wide range of temperatures in some temperature window, you can assume that CP and CV values are constant. See, though they depend on temperature, the function happens to be such that for some range of temperature, it is dependent on, I mean, it's independent of temperature, wide range. That's what we are doing. Okay. So we'll see that in
Okay.
problems. So first question from 5.1. So please solve. Simple question. You should be able to solve it. See, we know that delta H is integral T1 to T2 NCP dt, where N is the number of moles. But in the question, number of moles are not given. Mass is given. Then atomic weight is also given. So you can convert the mass into number of moles. So this is 1000 by 63.5. This comes to about 15.75 moles. So delta H, let's calculate. Please remember, temperature should always be in Kelvin. So this is room temperature. I'm taking 25 degrees centigrade, which is 298 Kelvin, and 100 degrees centigrade, which is 373 Kelvin. So 15.75 CP value is given as 44.35 kilojoules. So I'm just leaving it that kilo as it is so that you can answer the question in kilojoules. So this is 15.75 into 44.35 into 373 minus 298, which is 75. So the heat will be 5.52.4 megajoules. All of you have got that? Any doubts? Everyone got? Okay. Let's do the next problem. Now, please understand here that the CP value is given as a function of temperature. Now, whenever such questions are there, you have to be careful with the integration. Okay. So, I don't know what you have done so far. Let's see. CP is now a function of temperature. It's very clearly given that 3.6 plus 5.1 into 10 power minus 40. Units are very, very important. Kilojoule per mole per Kelvin. Okay. Now he says that when 1 mole of the oxygen is heated from room temperature to 100 degrees centigrade, what is the change in the value of enthalpy? So this is 298 to 3723. 1 mole is there, 3.6 plus 5.1 into 10 power minus 4 T dt. Okay. So individually you can expand 3.6 into 373 minus 298 plus 5.1 into 10 power minus 4 by 2. This is T dt is T square by 2. Na? So this is 373 square minus 298 square. If you do this, of course, you